early, but I might just make some introductions to begin with. My name's Ian Taylor. I'm a director here at FlowJo, and today I have the pleasure of giving you guys a demo of concatenation, t-SNE, or t-distributed stochastic neighbor embedding, and then the clustering that accompanies that in FlowJo. If you guys have any questions about the software or about our various tools, here's some different resources you can utilize to self-help if you need to. There's also an email address there, techsupport@flowjo.com. My email here is taylor@flowjo.com. If you have questions for me after the presentation, feel free to shoot any of those questions to us. There's also a Q&A panel within Zoom, which you can use to submit any questions while I'm going through these slides, and also going with the demo that I'll give after this brief presentation. So just an overview, we're going to go through the process of concatenation. We're going to perform a t-SNE clustering, a t-SNE mapping, and then we'll be clustering on that t-SNE map. And I'll demo some of what the color mapping feature can do in the latest version of FlowJo. I'll also show you how to compare different samples that you've concatenated within the t-SNE space. And then, like I say, I'll do a little demo where we try and walk through all those steps live in FlowJo. So the concatenation function in FlowJo is meant to combine multiple subpopulations or even whole samples together into one data file so that they can be analyzed just as you would a single FCS data file. It essentially is a new data file with a new parameter called sample ID that will allow you to separate out the different populations that you've combined. So once you've identified some populations in FlowJo that you're interested in, we'll see a little bit of this in the live demo. You're going to go ahead and select those nodes representing the populations of interest, and then you're going to right-click and choose Export Concatenate. Once you've done that, you'll be looking at a dialog similar to the one here on the right, which is going to show you two different tabs, either Export or the Concatenate option, either of which is going to create a new data file, the output of which will be at the destination shown here, using the format that you've chosen. FCS3 is recommended if you're going to reload the data into FlowJo, although CSV is also an option. And you'll want to know exactly where you're exporting that concatenated data file to. In this case, it's going to go to my Downloads folder. When choosing your parameters, you may have a subset of parameters that you're particularly interested in. If your data has a acquisition-defined compensation matrix already applied to it, we recommend you use all uncompensated parameters. And this will actually still include your acquisition-defined matrix in the resulting concatenate, where you'll see your data is compensated via that acquisition matrix. Otherwise, you're compensating via a matrix you've designed in FlowJo. All compensated parameters may be another good choice. Once you've finished setting this up, I've named my export total data set since we're concatenating all of the data files here. You'll see that at the bottom of that window, you get a little status that tells you what you're about to produce. In this case, we're getting exactly what we want, one new data file. So from there, you can go ahead and concatenate, at which point FlowJo is going to prompt you with a window asking whether you want to import that data file into a new workspace or into your current workspace. One tip I would give prior to reaching this concatenation window, if you've selected a population of interest and you're combining, in this case, all of our CD19 positive populations, choosing select equivalent nodes from the Edit tab in FlowJo's workspace will allow you to select all of those CD19 positive populations like we see here. And then it's just one simple click to right-click on the data or on the population, excuse me, and choose Export Concatenate. But that select equivalent nodes is a big time saver. Once you've combined your data, we're on to the t-SNE portion. So basically now we want to look at differences in populations within that data file in an unbiased fashion. And that's the whole purpose of t-SNE. To access the t-SNE platform, it's actually implemented as a plugin within FlowJo's workspace. So what you'll do is, in this case, we've already selected our total data set concatenated data file. And you'll go to the Workspace tab where you'll see a Populations ribbon. And from there, you'll choose the Plugins option and then finally select t-SNE. Once you've done so, you'll get the window that appears on the far right of this slide, which just gives you the various different options for performing tSNE. The crucial ones I want to point out here right away. Number one is your sample ID parameter, which I mentioned would be created within the newly concatenated data file. This will allow us to separate out the different samples that we've combined into this concatenated data file. You would not want to utilize this for tSNE, or else you will severely bias your tSNE clustering towards the individual samples that you have combined. You'll also notice that all of the compensated parameters have been selected, and this will be done by default by the tSNE plugin. However, we already utilize the CD19 parameter as well as the live dead stain to define our population of interest. So we're not as interested in exploring those two parameters. So I've eliminated them from my choice here. Again, you'll see more of this during the live demo for more details. You'll then name the tSNE parameters that you're interested in. By default, it'll name them tSNE, which is probably appropriate. For iterations, the best mapping is going to happen at the highest clustering number. I typically choose a value around 1,000 for kind of robust clustering. Perplexity is also something you typically want to increase to a point. It depends on the number of cells that you're clustering, and this can be a little bit finicky, so you may have to run tSNE more than once in order to find the optimal perplexity that you want to set. And then these other options, such as theta and learning rate, or eta, are more like fine-tuning. So if you're not able to get the kind of clustering that you're interested in, you're not getting enough clusters, or your clusters are too diffuse, you can go back and make some adjustments there. Again, running tSNE more than once shouldn't be any problem, as long as you're getting newly named tSNE parameters, and these will appear as derived parameters within your data file. Once you've set all of these settings in the tSNE dialog, you're going to go ahead and calculate, and that calculation can take a long time. It is a very computationally intensive algorithm that's being run. We have a question coming in from one of the listeners. I'll read aloud. How important is it to concatenate an equal amount of events from each sample? Will tSNE get influenced if some samples have more events than others within the concatenated file? I think that's a very fair, that's a good question, and it's a very fair concern. I think in some cases you certainly would be concerned with the bias introduced by oversampling from certain samples or populations. If you're looking for exceedingly rare events, it may be desirable to include every last event that you can. So I don't think that there's a hard and fast rule on this, but it is something to be aware of. I was actually going to note this in my tips and tricks. You can perform a downsample step for concatenation if you want to include only a certain number of events, maybe the number of events in your smallest population when you go to concatenate. So the downsample plugin, which is actually illustrated here in this list of plugins, is a really useful one for for people that want to normalize the number of events that they're including from each population or from each sample. So absolutely, great question. Keep those coming. And with that, I'm going to move on to my next slide. See here. So we've obviously completed the calculation for tSNE here, and I'm just visualizing my two new parameters created from those calculations, tSNE-X and tSNE-Y. And I'm showing this in the layout editor, so I've slightly modified the name. By default, it's going to tell you your iterations and perplexity and the other settings you had for tSNE within the parameter names. For clustering now, this is just basically a fancy word for gating. Some people prefer to call it filtering. But the whole idea of running tSNE is to make unbiased clustering decisions, or in other words, to make to delineate your different parameters without having to go through and manually set, whole hierarchies of gates. So in this case, I've chosen a particularly unbiased clustering tool called the AutoGate, which is basically density-based gating, and it gates based on contour lines of your data. So we can see that this island or this population in the top right-hand corner of our tSNE is easily delineated by the contour lines around it using this AutoGate tool. But of course, you can also use manual gates. So if you look in the bottom right, I've just used the pencil tool and drawn a gate around a set of populations that I'm interested in exploring. And that's basically how you're going to cluster these different events in FlowJo. Color mapping is another really useful feature once you've done the t-SNE mapping, because you may not have any idea, you likely have no idea what any of these clusters actually represent. So by checking that option color map axis in the bottom section of the graph window, you can actually color map the various islands by a tertiary parameter. In this case, we're looking at a CD14, a monocyte marker on the far left, which is showing us that that population I gated manually may actually contain monocyte events, although it looks like it's not very pure. In the middle graph, we see CD3 is being color mapped. And so we can see some islands that we may want to gate on if we're interested in T cells. And in the far right graph, we see a sample ID. So this is the parameter that separates out our different samples. And what we should see there, if we've done good t-SNE mapping and we're not too biased by the individual samples, is a randomization of these colors. And I think here, this illustrates that pretty well. So we don't see like a clump of red events anywhere that would indicate that our final population is biasing the whole mapping or any other color for that matter, because that can happen. And if your samples are distinct enough, they may be clustered out by t-SNE, and that might not be a huge issue. But especially if you haven't done something like downsampling ahead of time, you might be worried that the mapping will be biased by a particular sample. Next, just to cover probably one of the main use cases of this t-SNE on a concatenated data file, people that want to investigate the t-SNE clustering by sample. So as I mentioned, there's a sample ID parameter inserted into any concatenated data file, which allows us to gate out the various different samples. And the order of these samples will actually be the order of the samples as they existed in your workspace to begin with. So in this case, we had the very first sample was sample A1, second sample A2, so on through A9. And I've gone ahead and drawn those gates here. And now we can view the same, we can view these parameters in different graph windows, but utilizing the same t-SNE mapping. So that can be really handy. If we were to do this in a different order, if we were to run t-SNE on each of these individual samples, we would actually get a different t-SNE map for every sample. And so obviously that's going to make it impossible to compare between the different samples. And that's the whole reason for concatenating the data files ahead of time. Once you've done this gating, again, you can view those t-SNE parameters by sample. And we can see, for example, the very first A1 sample seems to be missing a lot of the population that we identified as potential monocytes. Similarly, looks like A5 has a similar grouping, like very few cells in that set of islands. There's all sorts of inferences you could make once you've kind of begun to dissect these different islands, these different populations within the t-SNE mapping, and then look at those across all samples. So that's that. As mentioned before, if you do have large data sets or you want to normalize the number of events in each population, you may want to consider downsampling prior to the concatenation process. As mentioned, this algorithm is quite computationally intensive, and so it's not uncommon for the calculation to take minutes or even hours. I've even had data sets of 1 million events that take a whole day to do t-SNE clustering or t-SNE mapping. So downsampling in that case is probably going to be required if you want to get your analysis done quickly. With that, I'm going to ask if there's any questions before I go on to demo this live. And again, feel free to drop those questions into the Q&A section of the Zoom window at any point during the demo as well, and I'll try and address any questions you might have. And again, here's some help links. I'll try and leave those up in case you guys want to reference them later. Okay, so here's our FlowJo workspace. If you haven't already gone ahead and downloaded FlowJo, you can access it from, just go to the FlowJo solutions section, and then the downloads tab will be available there. I'm getting a question from one of the listeners. Is t-SNE computed after logical transform? That's a really good question, actually. You should have your scaling set before doing any gating or t-SNE calculations. So that's absolutely required. That's because the transform data is what, or the bend data is what the t-SNE algorithm is going to utilize when completing the mapping. So if your data is incorrectly scaled when you do the mapping, you're very likely to get an improper mapping. I'm getting another question. If you have many samples, 50 or so, would you recommend taking fewer events per sample and including a higher number of samples, or the opposite, taking more events from fewer samples? Yeah, if you have 50 samples that you want to compare in the same t-SNE space, you are absolutely going to need to use all 50 samples. Now, depending on the size of the samples, you may want to gate down to a subset that you're actually interested in. So you might have some markers that you know a priori you're going to be investigating. This would be a really good way to reduce the number of events in each sample. But if at the end of that gating, maybe you still have way too many events, or your t-SNE calculation after concatenation is taking a really long time, then yes, absolutely, you would want to consider downsampling even the subpopulation that you've arrived at prior to concatenation. Another really good, you guys are coming up with great questions. Another user's asking, why use uncompensated when concatenating? Yeah, so as I mentioned, I kind of brushed over this, but if you have an acquisition-defined compensation matrix, then what you really want to utilize is that acquisition-defined matrix in your concatenated file. And if all of the data files share the same the same acquisition-defined matrix, then post-concatenation, you'll still have access to that acquisition-defined matrix through the spillover keywords in your data file. So that's why I used uncompensated parameters for concatenation. If I was to choose all compensated parameters instead, what I would get are parameters that are pre-compensated by FlowJo. In other words, the spillover would have been subtracted from those parameters explicitly, and I would get new parameters with the prefix fjcomp. And that just means that they were compensated in a previous workspace in FlowJo. So that's certainly something you can do. And if you've done compensation through the compensation wizard in FlowJo, you might want to consider it, because that matrix won't be imported through the keywords of your data file. So yes, frequently we recommend choosing uncompensated parameters if you have a acquisition-defined matrix. Otherwise, compensated parameters can be just fine as well. You can also export your FlowJo compensation from a workspace and then re-import it, but that makes for a little bit more tedious process if you are having to do that. So back to our workspace, I'm going to go ahead and load some data. And to do this, I'm actually going to use a new tool we have. It's the FlowJo Envoy vehicle here. And to access it, you would just click Add Samples and then choose the Envoy option there. You will have to have an Envoy account to do this, and you will have to have already loaded some data. So you can see in the FlowJo core, in my lab, we've already got a concatenation t-SNE demo data set here. Oh, excuse me. I'm actually going to go back a step and load that workspace. So again, to access a workspace in Envoy, if I go to the File tab, I can open from Envoy, and just take a moment to ping the server and then give me back that browser window. Maybe more than a moment. And this is just a workspace where I've preloaded some demo data that I'd like to go ahead and gate and then concatenate and run the t-SNE calculation on. There we go. Demo workspace, that's what I want. Normally this is a little quicker. I think I must have Wi-Fi wherever I'm at right now. In fact, I might even have a So as soon as this is downloaded, I'm going to define some populations, probably just do like a size gate, gate on live events. And then I think there may be a monocyte marker in here that I can use to gate on CD14 positive events. And those are the ones that I'll use to, for tSNE. While we're waiting, feel free to drop any questions on me you might have at this point. All right, sweet. So here, maybe this is our size gate of interest. From there, I'll look at a histogram for live dead. It looks like our scaling is already off. So I'll go ahead and rescale all of these compensated parameters like so. And maybe by X, that width basis looks a little bit large to me. Okay with that. Here's our live events. And if I hold down Alt, I can just drag this up to our group. Now those have been applied for all. Let's make sure that this gate is appropriate for those samples. It looked okay to me. I might even just check that the scatter doesn't deviate too much. Ooh, that one was a little bit off. Cool. Now, if I open up that set of live events, what kind of markers do we have here? I was wrong. There is no monocyte marker for this data set. That was the other data set. And maybe we'll go with T cells. Great. If I apply this to all the live events, I should be able to scroll through and make sure that looks okay. And indeed, it looks like it identifies the T cell population well. So now I do see a problem. This is going to be a huge number of events to, once concatenated, this is going to be a huge number of events to tSNE live. So I might just downsample this so that I'm only looking at about maybe 9,000 events for, well, we could go higher than that. How about 18,000 events for the total sample? So just to demo how this tool would work, go to the workspace. Include no more than. Yeah, okay, I'm getting another question, sorry. User's asking, can you use the include no more than function instead of downsampling when concatenating? Actually, you can't. The reason being that feature actually has a problem currently. So it's something we're hoping to fix in a future release. For the time being, we recommend using the downsample option. The downsample option is actually a little bit nicer than the include no more than, because include no more than means it will include events in the FCS file according to their acquisition time. So you're slightly biasing your data set towards those events collected first. And there's probably no reason why that would hurt, but it would be better to take a random sampling, which is essentially what the downsample tool will do. But again, a really great question there. There's something wrong here. Okay, well, let's make sure, yeah, you bet. Let's make sure that we have the plugins installed correctly. So I have FJ plugins on my desktop, there it is. And it looks like I'm missing some of the critical plugins. So excuse me for a moment here, I'm just going to recover my download here. Let's move that onto the desktop. See how quickly we can get plugins back. So if you just drag your, once you've downloaded our installer and you're trying to install it, you should be able to just drag and drop those plugins wherever you want to see them. In this case, I would like to add tSNE and downsample. Oops. I'll just copy those because I want to add them to my plugins folder, which is right here. Now this will actually, oh no, this will require that I restart FlowJo to see those plugins show up. They're not going to be there yet. I'll go ahead and save this workspace. right, should be back in action in no time. And now we know we want to open that workspace. And I'll go to my particular project, which in this case is the FlowJo core, and my lab, which is the Taylor lab. And it's just this first workspace here. Now back to this downloading. Any more questions while we wait? Only a moment more. Another user is asking if there's any limit to the number of parameters you can use for t-SNE analysis. There isn't. You should be able to calculate t-SNE for thousands of parameters in theory. We actually utilize this tool in another software that we've produced very recently, SeqGeek, which analyzes single-cell RNA sequencing data that can have, I've seen data there with 60,000 gene parameters, and you can run t-SNE on that data. So there shouldn't be a limit. There might be a practical limit in terms of the time that the calculation will take. As I mentioned, this is computationally intensive, and the more parameters and events that you're trying to perform the mapping on is going to increase the amount of time that that takes. So yeah, really good question there. The other thing you can do, for example, in that software is run PCA first, so prior to t-SNE, and then t-SNE on those principal component parameters. But that's probably a conversation for another day. Feel free to write in if you have questions about either SeqGeek or performing t-SNE on huge numbers of parameters. So let's try this one more time. If I go to the Workspace tab, now my plugins contains a downsample tool, excellent. And in this case, I think I want to include 2,000 events from each of these samples, or from each of my T-cell populations, excuse me. So you can see very quickly I've calculated a random set of T-cells, and I'll go ahead and do that for all of these samples. Once that's completed, it looks like it has, I'm going to select that downsampled population and then combine them all. So again, the shortcut here is select equivalent nodes. That should select all of our downsampled populations. Now if I right click, I can simply choose export concatenate, and that will bring up this concatenation window that we've seen before. I'm going to choose concatenate, and I actually want this to go to my downloads folder, so I'll change that. We notice here that there's an acquisition defined matrix for all of these samples, which I happen to know is in common for all of the samples. So I'll just use the uncompensated parameters again. I want to call this something a little more descriptive than concat, maybe total downsampled pops. And it looks like we're going to generate one new data file, and that's exactly what I want to do. So I'll go ahead and concatenate. And I'll open that in this existing workspace in case I ever want to compare with something happened there. Let's make sure that this will work. Oh, cancel this. Looks like something went wrong with my combination. Let's try that one more time. And now I would like to concatenate. I'll leave the name the same. And open in a new workspace. Let's see if that will work. Okay. Didn't throw any errors there, so great. Not sure what happened in that first instance. I'll have to investigate a little bit later on. But we've generated a new concatenated data file that contains 18,000 events randomly from those tSNE populations that we identified previously. Now let's go ahead and perform the tSNE mapping so we can cluster on the data. So again, if I've selected the data file, I should be able to access in the plugins tool the tSNE option. It'll ask you to save your workspace before you calculate tSNE. This is so that there's a location where all of these tSNE artifacts can be located. And in this case, I'll put it in my downloads folder again, where I like to place stuff. We'll call this the, demo workspace. And you'll notice that all of my compensated parameters have been selected. But as we saw before, we've already utilized the live dead stain. And we also isolated T cells. So the CD3 parameter is not going to be necessary for this tSNE clustering, or it's not going to add any extra value. Might increase this perplexity, although it will increase slightly the time that it takes to calculate. I don't need to generate a movie. That's just going to create a whole set of SVG files that we could utilize to create like a live movie of the clustering occurring, or the mapping occurring, excuse me. And that all looks good. So without further ado, let's start the calculation process. Now this is expected to take at least a little while. So we would welcome any questions that you might have at this point. Apologies for the delay in getting here. A couple of technical issues there. By the way, if you are running into any issues like the ones that we've seen, feel free to write to techsupport@flowjo.com and someone will get back to you as soon as possible. We have a really nice quick turnaround time there. You can also write to me, and my name's Ian, and my email address is taylor@flowjo.com for any questions or concerns. Didn't check by X transform here. But the data should have been, that's a really good question. The data should have been transformed ahead of time because we actually went through and made sure that all of our parameters were by exponentially transformed. So let's just double check that that was the case, because it's possible I missed something there. So yeah, so you can see here in the live dead stain that we are looking at values below 0 and everything looks correctly transformed. Hoping my width bases stayed still at about 10. Yeah, -10. So all of these parameters were transformed in a previous step. And I might note, there might be some confusion here. The bi-exponential transform is only for the flow parameters, the data that you're going to be performing the mapping on, not on the tSNE calculation itself. The tSNE is going to wind up being linear in the new workspace. Yeah, let's check that out. So sorry, same user's asking or pointing out that I'm not checking that in the new workspace, so let's check that out. Good point. And this could be a problem. Looks like bi-X was chosen and the same width basis. So that's good. I don't know if those preferences were saved to my population, to my workspace, or to the preferences. Getting another question here. What would the difference be if you selected CD56 instead of CD3? So in that case, our concatenated population would be CD56 positive instead of the CD3 positive events. Great question. So yeah, if we weren't interested, instead we're looking at those CD56 positive events as a population of interest, then that would be just fine. In fact, I mean, we could have, if we had 20 markers and many more events, we might have wanted to drill down to something very specific, and then you could run tSNE on whatever parameters were left. But you typically wouldn't, I think you wouldn't want to run tSNE on parameters that you've already used for gating, because you've already gleaned the information that you're interested in from those parameters. And so that's why I excluded CD3, because we already know that the populations that we combine are our CD3 positive T cells. So absolutely. All right, so the calculation just finished, but I've got one more question. What happens if you have some non-matching parameters in one of the channels? If you had non-matching parameters, we would have run into problems potentially in an earlier step. Essentially, when you do the concatenation, only those parameters in common for all populations selected will be included in the concatenate. In this case, all of them were in common, so we got all of those parameters. Oh, I see. I've been neglecting the chat window. There's another set of questions here. Can you do the t-SNE analysis on Boolean gated populations? Yeah, there shouldn't be any restriction on the type of populations that you're running the t-SNE analysis on. Trying to think of any concerns there. No, it should work just fine. In fact, you could have done Boolean analysis to arrive at a population of interest, concatenate those files, and arrive at your concatenated file. So once the t-SNE has finished calculating, you'll notice we get two new artifacts. These are our two new parameters. They're derived parameters, and if you double click on them, they'll look a little different than your normal derived parameters. That's because these derived parameters are actually written to a CSV file elsewhere on your machine, and FlowJo is just calling out to that CSV file in order to pull in these new parameters, but it's not an ordinary algebraic kind of parameter. And so you get this little error. It's nothing to be concerned with. Another thing you'll notice right off the bat is that we're looking at a linear scale, which is as expected. So the t-SNE mapping is done into a linear space, and it should do its best to separate out different populations in an unbiased fashion, and that's really important. So let's close down some of these other graph windows, and we'll investigate the t-SNE just a little bit as kind of the final hurrah here. So t-SNE X, t-SNE Y. And so this actually arrived at really nicely delineated islands where we see different potential biological functions occurring. And we could easily gate on those in using the AutoGate tool. Now, I particularly like the AutoGate tool because it is so unbiased. It's just going to gate based on the density of a certain area. So like I say, the contour lines is what it's actually using. And if we look at a contour plot, that should be really clear. So here's our different contour lines, and we can see if we're pulling out this island, it's going to stick to the contour lines. So let's just call this P1 because we don't know what it is at this moment. We can always rename it if we decide that this is something of interest. Another question. Can I change the axis to zoom in? You can do that. You typically wouldn't want to, I think, especially for the t-SNE parameters, because anytime you change a parameter scaling, it changes for all instances of that parameter in other samples as well as in the different populations within a sample. So it's something you could do if you really needed to zoom in on a population, but typically you would set the parameter scaling the way you want it and then do your gating and not do any zooming in after the fact. So I hope that answers your question. So we've got a P1 identified. Maybe we'll just do a couple more before we move on to looking at the different samples. So this will be our P2 island population. And maybe something a little further away, like this little guy here. Call that P3. And again, we might investigate and figure out what these are, and we could rename them, or things of that nature. We could also dig into these populations. We could look at what other markers are expressed there, or if there are subpopulations. You can even run t-SNE again on a secondary population. So here's another question. User's asking, if you want more or less clusters, which t-SNE parameter would you change? The complexity? Good question. If you wanted less clusters, I would suggest reducing the iterations, and vice versa. If you wanted more clusters, you could increase the iterations. The perplexity is the other parameter I would probably suggest altering next. You do have other options like the learning rate and the theta, which you could adjust, but that's going to be much more fine-tuning the t-SNE mapping that you get. But absolutely, you can run t-SNE multiple times on the same sample, or even running it again on, sometimes there's a subset that's quite large, and you may want to run t-SNE again on that subpopulation to do further exploration and discovery on it. Also depends on the number of parameters, right? Because here we only have a few parameters. It's probably not a huge deal to look through them all once we've done t-SNE. But in some cases, that will be a challenging task. So speaking of other parameters, we've identified a few different populations. Now let's look at how the different parameters look heat mapped onto or color mapped onto this plot. In order to do that, I'm going to check this box for color axis, and it's automatically going to color by this first parameter, CD56. And what we see is the range of CD56 isn't widely varying. Maybe there is something under P1, I'm not sure, no. So mostly green events, I'm not even seeing red events, which means we don't have a lot of high CD56 events in this data set after getting on CD3, should keep in mind. What else might we want to look at? We could look at our helper T cells, and I'm suspecting that maybe these islands here, maybe P3 is one of our helper T cell population. We also see a lot of sort of like dim events here. Or sorry, excuse me, I got that totally backwards. These are our helper T cells, excuse me. And these are more dim, and here's our lowest, right? Anyway, so this is very stark, you can see. I might, instead of removing this because it's so beautiful, I might just keep it open and check out another. Maybe now we're interested in our killer T cells. So there you go. Now these are looking like maybe, in fact, these are more like, we know these are sort of dim for the CD4 population. Maybe these are our naive T cells. Maybe they're double positive. And then in that case, maybe these are our killer T cells. If that makes sense. One last thing before I move off of color mapping, I'm going to duplicate this window and move it over here. And I'm going to look at our sample ID just to make sure that everything looks, relatively unbiased, because obviously we don't want one of these clusters containing all of a particular sample. That would mean that that cluster was, there was something going on in that sample. And when we do that, we can see that we kind of get a spread. We have red events in each of these clusters, which is going to come from our very last populations. And we have green events, which are going to come from the middle. Probably there are blue events in here, although I don't see them well here. Something else is distinction by sample. So while we're talking about samples here, let's change this to a histogram of sample ID, which will allow us to distinguish between our different samples. Now here we've done downsampling, so as opposed to the slide I showed, which I might just go back to, maybe. When we separated out these different samples, you can see I didn't normalize. I didn't do any kind of downsampling before I concatenated, and so we have different numbers of each of the different samples. Here, since we did a downsample, we know that there are 2,000 events in every single one of these sample populations. So this being our sample 1, I believe it was actually called B1. So our second row of our plate of data. And here's B2, roughly, etc. I might just go 3 samples because that's probably all we'll need for demo purposes. B3. And at some point we may implement a plugin that would allow this to occur automatically via auto gating, so you could have FlowJo gate out the different samples, but currently that's not available for FlowJo. It is, however, been implemented in SeatGeek. So that's great. If we wanted to view these different parameters in t-SNE space, there's a couple of different ways that we could do that. The way I'm going to use, the way I'm going to show it is in the layout editor. So if I switch from X and Y, now remember we're looking here at our B1 sample. We can see that the t-SNE mapping is much sparser because it only contains the events coming from that very first sample. If I drag that into the layout editor, we should see the last plot I viewed. And that's great. Now a trick, if we want to bring in a couple more samples very quickly, is to simply hold down the Alt key on my keyboard and then drag this, and that will create a copy of that plot. But if I want to see another sample here, I can just do an overlay. Actually, might overlay both of these. And then I'll remove the sample I'm not interested in. So in this case, I want to remove, say, sample 2, hit delete, and apply that. Now we have sample 1 all in red. If I do the same thing here and I remove sample 2, or sorry, sample 1 in this case, should have sample 2 all in blue. And that's how we could kind of compare between samples 1 and 2. Another question. Proliferation tool would help. Yeah, oh, I know what you mean. So what this user is suggesting is you could utilize the auto gating from proliferation in order to potentially separate out the different samples. That's an interesting question. I don't know if I want to try it in a demo here, but that actually might work. The only problem is I believe that tool is geared for log scaled data or bi-x scaled data. And in this case, it will be linear when you're gating on the sample ID. So I'm not sure that would do the trick. But again, I anticipate that we'll have a plugin for this sometime in the relatively near future. So hopefully we'll have an easy solution for that other than potentially running proliferation on a sample ID parameter. But that's that's a creative way to potentially do it. Absolutely. I think that's really all I wanted to demo. Let me just scroll through here. So you can see I kind of went through and made large dots to show these in my example. Is there anything else? Again, I might just want to highlight, oh, sorry, another question. Let me get to this. Could we change the color palette to double gradient palette? Transcriptomics, blue, red, white, red. You can't in FlowJo. You mentioned transcriptomics. I don't know if you're potentially a SeatGeek user or somebody who does sequencing, but you might check out the SeatGeek software, which is available from our website. And you can get a trial there for 30 days. Do let us know if you have any questions while utilizing that software, as it is fairly new. But and you can write to the same address, techsupport@flowjo.com for that, or SeatGeek@flowjo.com for help. It does have different color palettes for heat mapping. So if you were doing like a table of heat map, genes versus cells, then you could look at blue, white, and red scaled data. But you cannot change the color palette in FlowJo at this time. Unfortunately, no. Great question, though. It's an interesting one, yeah. Yeah, keep them coming. Just in the last few moments here. Oh, let's see. Somebody says they've already tried tSNE, same workspace, and noticed the tSNE recomputed automatically on some events. A live gate, for example. How do you avoid recalculation? Yeah, tSNE shouldn't recalculate when you reopen a workspace, and I think that's what you're describing there. How to avoid it? That's a tricky one. If you have a workspace that's continually recalculating tSNE, you could send that to us. We're always happy to take a look at specific users' data. If you guys are having any technical issues with the software, I would recommend maybe save that analysis as an ACS file, which is available. Let me show you how you do that. If I had this workspace and I wanted to do so, if I just go to Save As, there's an option here, Save As Archive or ACS. Send that ACS file to this address here, techsupport@flowjo.com. Just let us know you're seeing recalculation on your tSNE, and we'll take a closer look. It's a great question because, as I mentioned previously, tSNE is non-deterministic. And so if you are recalculating, you're expected to get a different mapping of the data once that's completed. Sorry, clarification here, same questioner. It's not upon reopening the workspace, but when adjusting a gate, for example. So I'm assuming, and correct me if I'm wrong here, but this is probably an upstream gate to your population of interest. In other words, you're changing the events that are being used to define the t-SNE mapping, in which case FlowJo will need to recalculate. Reason being, the t-SNE mapping is determined by the events that are contained in the population of interest. So if you change that population, FlowJo has to figure out what is the new t-SNE mapping for this new set of events. So I'm afraid if that is the case, if you're changing an upstream gate, it's probably unavoidable to have to go through that recalculation. And what that means, I suppose, in terms of workflow, is that you just want to make sure that your gating is completed and correct before you run the t-SNE calculation. That's a great question on both fronts. Allowed me to highlight some tech support and also to talk about changing the parent populations of a t-SNE mapped population, because that's kind of a, you would want to avoid that as much as possible. Yeah, so asking about applying the operation in a new workspace. You shouldn't need to. I think this is in reference to the previous question, but yeah, you can apply t-SNE at any point in your gating hierarchy, and it should be fine. But if you make adjustments to that gate, then you're going to have a recalculation problem potentially. So if it's something where you need to adjust the gates and you're concerned about the t-SNE being recalculated, you could do the t-SNE on a exported data file in a new workspace. But in that case, when you do your adjustment to the parent gates, that won't apply to the exported population. So I'm not sure if that gets around the problem, but it's maybe an interesting thought to export your data into a new workspace. Oh, another question coming in through chat. Somebody's asking if they could get access to these slides. And the answer is absolutely yes. Again, just you could write to me, write to taylor@flowjo.com and request the slides from the concatenation demo today. And I'd be happy to send these over to you. That'd be no problem at all. And then you'll have access to all these resources and some of the demo slides. Yeah, that's absolutely available to you. I would also note that this webinar will be posted at this location in the FlowJo.com Learn tab under webinars. I think I got this website a little wrong. Yeah, so FlowJo.com/learn/webinars. You'll see a list of pre-recorded webinars from other demos, and this one should be added to that site once we're completed here and we get it downloaded. You'll also see a list of future webinars that will be hosted. We do some regularly scheduled webinars that kind of just on repeat, but we also do cool new sort of feature request type webinars, such as this one, where we show off the latest and greatest sort of tips and tricks for FlowJo, as well as our other products such as SeatGeek. So you guys should definitely check that out. If you have questions and you don't want to have to write in, you can always check out our documentation pages at docs.flowjo.com. In the case of FlowJo, you'll go to the /D2 option there. And we also have a FlowJo University site that kind of just teaches users, researchers, how to analyze data and utilize all the features in FlowJo. So those are all really great resources, which I would encourage you guys to check out. And if that's all, nope, got one more. For installing the plugins in Windows, do you do that in a different way? And what about plugins that link to R? How do you install it? That's a fair question. I'll go through it a little bit. I don't want to get into too much detail as there's a little bit involved doing R-based plugins. But as far as installing on Windows, a few of the plugins should come by default. So once you've completed the install, you'll have a plugins folder that's within the install directory for FlowJo on your Windows machine. So that'll be, by default, it's going to be in your program files folder, a folder called FlowJo space V10. And that's where all of the plugins are going to be by default, including downsample and tSNE, the ones we've covered today. If you wanted to check out other plugins, you can always go to exchange.flowjo.com, which contains all of our plugins, along with a lot of documentation specific to those particular plugins. And I would encourage you to check that out. Once you have downloaded those plugins, if they are R-based, I'll just show you. If you open up the preferences in diagnostics, there's actually a section here, scan for plugins. So in the case of this Mac, I have the plugins on my desktop. On a Windows, this will be slightly different. But the R path here has to point to, in the case of the Windows system, it will want to point to the executable for R. So that'll be in the R bin and then the bitness of your machine. So either x64 or x86, I believe, if you're on 32-bit. That's a tough question. And again, if you ran into any trouble in installing FlowJo, the plugins, or R, I would encourage you to write into tech support, and we'll be happy to help you with that. Absolutely. That can be really difficult for especially beginning users, people that aren't accustomed to R. Yeah, you bet. All right. Well, you guys have been a great audience. I really appreciate all of the questions, and I'm really psyched to be here to give you this presentation today. Again, feel free to reach out if you have any further questions and check out our next set of webinars. Thank you all again. Bye now.